Welcome to chapter 3, Properties of Pure Substances. So this is the objective of this chapter. At the end of the lesson, you should be able to achieve all these points that is being written down here. You can just go through by yourself. Now, pure substance. What's a pure substance? Pure substance has a fixed chemical composition throughout. Okay, example, if it's nitrogen gas, then the whole thing is nitrogen gas. So even if the nitrogen gas is actually in vapor and liquid form, it is still known as pure substance. Okay, now for thermodynamics, air, we know air is made of nitrogen, oxygen, carbon dioxide and few other gases. But then in thermodynamics book, air which is in vapor phase, means air is definitely in vapor phase, right, is known as pure substance. It's a bit unique, it's a bit unique. But then if you compress the air and if you have a liquid part of the air and also air, then this is not pure substance. Okay, you get it? Only air in the gas phase will be considered as pure substance. Okay. Now, chapter 3.2, phases of a pure substance. So we have 3 phases. Actually, we have 4 phases, but then in this syllabus, in this thermodynamics lesson, we only discuss on 3 phases, which is the first phase, the solid phase. In solid phase, atoms are actually arranged in a manner, in a fixed position, in a lattice. Can you see it forms a nice, unique arrangement, and it's fixed. Whereas in liquid phase, it's not in a fixed position, but it's still close to each other. It can freely move. Now, in gas phase, it is randomly moving. It's randomly moving. Okay. So in gas phase, like what I've explained just now, it is randomly moving and there are a lot of void spaces in between, but then based on thermodynamics lesson that we have done in chapter 2, we apply the continuum theory. Okay, next we're going to move on to 3.3. We're going to look at phase change of pure substance. So state 1, this is like a story, a continuation story from state 1 moving to state 2 and so on. I want you to pay attention and really understand what is the states of the liquid itself. So the first state we have compressed liquid, okay, which is known as also as subcooled liquid. It's a substance that is not about to vaporize. It means at 1 atmospheric pressure, example like water at 20 degrees C, it's known as compressed liquid. Now you introduce heat. When you introduce heat in a piston that's closed, but of course this boundary can move, so what happens? The water will start boiling, right? So it will attain 100 degrees. When it attains 100 degrees and is ready to vaporize, is known as saturated liquid. It means it haven't vaporized but about to vaporize. Okay. Next, from state 2, you keep on introducing heat. It will get into state 3. Now in state 3, what happens is that the liquid that's about to vaporize will start vaporizing, forming two layers, 2 states. I mean two phases, which is one is vapor phase and the other is liquid phase. Okay, because heat is constantly being introduced. Okay, what happens here is that this liquid will start fully becoming vapor. So that is what in state 4. It becomes saturated vapor. So it remains 100 degrees until the last drop of liquid is vaporized. Okay, so this would be saturated liquid vapor mixture and this is known as saturated vapor. Now, if you keep on giving heat, from state 4, you are moving to state 5, what happens? More heat is transferred, the vapor will become superheated vapor. Okay, superheated vapor. So if you see, this is vapor phase, this is also vapor phase. Okay, so all the state 1 to state 2 to state 3 can be represented in a TV diagram, temperature volume diagram. Yeah, so we have compressed liquid, yeah, compressed liquid, and then we have 2 to 3 to 4, that would be the, what phase is this? This would be the mixture phase, where you have fully here 100% liquid and then fully here 100% vapor, whereas this state here will be a mixture. Okay, what is happening here? The heat that is transferred is used to raise the temperature here, to raise the temperature, whereas the temperature, the heat that is introduced here is used to break the bonds. Yeah, to break the bonds, and this is more known as the latent heat. Yeah, this region is known as the latent heat. Okay, now when fully liquid, fully vapor, what happens? The energy that's transferred is used to increase the temperature once again from 100 to 300 to your superheated vapor. So that is what is actually happening. Yeah, so saturation temperature and saturation pressure. This is a standard thing. It's written as Tsat and Psat. These two values, yeah, we're going to look at for pure substance. Yeah, it actually depends. Yeah, it actually depends on the pressure. You look at these. Yeah, this is for water. Water is a common thing, so we'll look at water. You see, at temperature 20, Psat is 2.34, whereas at temperature 100, Psat is 101.4. So it is very temperature dependent. Yeah, so that's why the graph that's plotted Psat versus Tsat, it will be a line which is curving this way. Okay, so next we have latent heat. What is latent heat? It is used for phase change. So we have two, fusion and vaporization. So let's label here which is fusion and which is vaporization. Like in this case, because the water is actually starting from 20, yeah, from 20 degrees C, we can't see the fusion, fusion. Yeah, because this is during melting. Okay, vaporization is during here, from liquid to vapor. So this is latent heat of vaporization. Remember, moving this side, it's absorbing heat. Moving this side is releasing heat. So the value would be a fixed value. Yeah, the value is a fixed value. Yeah, you will see it later. You see here, latent heat of fusion at 1 atmospheric is 337. And latent heat of vaporization is 2256. So if you are fixing at 1 atmospheric, yeah, for latent heat of vaporization, like this graph here, to vaporize the liquid, it needs what? What is the value just now again? 2256. Yeah, so it is 2256 additional. But to release it back to become liquid phase, it will be 2256, releasing it out. Okay, so that's how it is. And then, okay, this is just an example to show the consequences of Tsat and Psat dependent. Yeah, okay. Next, let's move on to 3.4. Okay, in 3.4, yeah, in 3.4, we're going to look at property diagram for phase change. Okay, now let's get back to this. Yeah, let's look at these. Yeah, okay, let's look at these. This line is plotted for what? 1 atmospheric. Yeah, so this line is plotted for 1 atmospheric. Look at this. At 1 atmospheric, this is the behavior. Okay, got it? Now let's look at this. Okay, so where we are. Okay, this is okay, 1 megapascal. Okay, 0.01. Okay, now let's look at this. This is at 0.01 megapascal, and this at 0.1 megapascal, and this line will be for 0.1 megapascal, and this line is from 8 megapascal. What do you realize? As the pressure is actually increasing, what happens to the latent heat of vaporization? It is actually becoming shorter. Okay, it's becoming shorter. Did you realize that? Okay, so if I were to join these lines, okay, like what we did in primary school, right? We take the dot, we join the dot, We join, and we bring it down here, and we join everything. It's like forming a curve, isn't it? Yeah, it's forming a curve. So this is a TV curve. Okay, TV curve. Okay, let's look at this. Is the same graph. Look, they are only drawing the curve. So in this curve, this line here is called the saturated liquid line, and this is the saturated vapor line. Why? You remember the region just now? Anything that's beyond here, yeah, because this point here will be the saturated vapor. Correct or not? It's about to change to superheated vapor. Yeah, and this is the saturation liquid dots. So you join this way. So that's why this is saturated liquid and this is saturated vapor line. So anything that's beyond this region here will be compressed liquid. Okay, you remember this graph? Okay, let me just remind you. See? So the curve is something like this, isn't it? If you redraw the curve, of course the upper one is not appearing here. So what region is this? Compressed liquid. What region is middle here? It is a saturated mixture. And what's the region here? It is superheated vapor. Now let's go back here. Can you understand now? Yeah. So these are the regions. This is compressed liquid region, this is superheated region, and this is mixture. And of course, when you're going higher up, okay, let's look at it. When you're going higher up, when you're hiking up, okay, I'm going to erase all this. What happens up here? It achieves critical point, and up here, you don't even have latent heat anymore. Correct or not? Yeah. So this is what is actually being plotted up here. Yeah. So this is called the critical point. Critical point. Yeah. Okay. At supercritical pressure, which is pressure more than critical point, there is no distinct phase change. So immediately from liquid, it is forming vapor. You don't have a change. Like, okay, like example, what I meant is like, if you take a pot of water, you boil, you can see it's forming vapor, and then slowly what happens is that the vapor will start the liquid will start boiling, and then it forms vapor, and then finally it disappears. But then in a critical thing, you don't have that change. It's immediately disappearing into vapor. Okay, so let me just repeat. This is your TV graph. Now, the same graph can be also plotted PV. But what happens here is that this would be reversed. Can you see that? Okay. Just now, this was pressure, isn't it? Now, this is temperature. Can you see that? Yeah. But this region is still compressed liquid. This region is saturated liquid vapor. This is also superheated. Okay. Everything remains the same. It's just that the curvature is a bit different. Okay. So, let's now move on to some diagrams of PV where you're including the solid phase. Now God is great. What God has done is that all solid will actually contract. Will actually contract when it's cold. Okay, what I meant is, you see, when it's freezing, most of the materials on earth will actually contract, become smaller, shrink. Okay, contract means it becomes shrink, except for water. Water expands when it freezes. Reason being because God wants aquatic life to be able to still survive when you have freezing activity up here. So ice actually floats on the water. So the graph that you have been seeing before this is between vapor and liquid. Now I'm going to add on the solid line. Can you see solid? And this is the solid liquid phase, and then we have liquid phase, and then whatever that you have seen just now. Okay, so adding. So for a solid that contracts, this is how the line will look. Whereas for solid that expands, the line is a bit slanted. Okay, that is the difference. Okay, now let's look at the next one, sublimation. So what is sublimation? Sublimation is when you heat up, solid immediately forms vapor. So in your daily life, what are the materials that goes through sublimation? Okay, your house, you can look at naphthalene. You know what's naphthalene? The the mothball, the one that you use for the cockroach, to prevent cockroach. Yeah, in the lab, you can look at iodine. When you put iodine and you heat up iodine, it will immediately vaporize. Yeah, okay. So now I'm going to introduce to you the PT diagram of pure substance. We are still working on pure substance. Okay. Now observe this carefully. Okay. Now the solid line, this line. Can you see this Y? It's a fork. Yeah. It's a fork like this. Y. Yeah. The fork is smaller. This line is for substance that contracts in freezing. Whereas there is another line that I'm going to draw. Observe this. The same thing, but the fork is bigger. Can you see? Now this one is for substance that is freezing. Yeah, the fork, the Y is even wider. Yeah, following the same line but is wider. Yeah. Okay, so this will be the PT diagram for the pure substance. Now if you observe here, there is a point that's called triple point. What is a triple point? A point where vapor, solid and liquid coexist at the same point. Okay, so that is known as the triple point. Yeah. Okay, the same diagram earlier, this is 2D. Yeah, this is 2D. If you to represent this, it will be in 3D. Can you see? This is a 3D diagram. Yeah, 3D diagram for substance that contracts in freezing, and this is for expands in freezing. Yeah, it looks very complicated, right? If you want to get numbers from here, it's going to be very, very difficult. Yeah, that's the reason why we have property tables. We'll go into property tables in the next video. I hope you have understood everything. If you have any issues at all, please do meet me during my consultation hours and ask me questions. Thank you. And also, please do read up your textbook. Yeah, only then you will understand it better. Thank you.